Hello everyone. Today we are going to start our second second lecture for the whole playlist, which we are making it for Foundation of Artificial Intelligence. So today we are going to learn how can we train these AIs and how they work, what data are required, and what kind of models are running in this kind of artificial intelligence. So we'll go through all like data, what kind of data, and learning, and also models, what kind of models are better into learning. So we'll come through all the scenarios of learning. So let's say uh, in this lecture, we will be completely going through core foundation of machine learning, and it's believe me, I will teach you guys like it is kind of a play school thing. It will be very enjoyable, and you'll have a good knowledge of understanding of machine learnings with aspects of how it is getting trained, what kind of data are required, what is the learning procedures and everything. And believe me, after this lecture, you will understand everything as a matter of with real world examples, and it will be very nice for you guys to understand and very easy for you guys to understand. So we'll start from why data matters more than algorithms. So why is it like data matters more and the algorithms matter less? Even though algorithms are the core principle of any machine learning model, still it matters not that much as the data is required. Because without good data, nothing is good. So let's say 87% of machine learning projects fail because of bad data and not bad algorithms. And think of it like baking a cake. So imagine, I'll give you a simple explanation. Imagine you want to teach a robot to recognize chocolate cake. If you show it pictures of stuff like random stuffs like pizza, car, socks, and but label them all that like they are all chocolates, then that robot will get confused, and doesn't matter how much you will, if you have the world's smartest cake recognizing brain, but it will be a garbage and it will only recognize that it is a chocolate. We put pizza, car, or anything because it was trained as it is all are considered as a chocolate. So if you are giving a data with a false informations, then your any kind of models or AI will reflect you the same opinions like a false opinions. So definitely it will work as how you try to provide the data. I'll give you a real world example now. So let's say there was in 2018 Amazon's hiring disaster. In that Amazon's hiring disaster, Amazon trained AI on 10 years of hiring records. Believe me, like 10 years of hiring records from their tech department, which was 80% of men. And the AI learned to say yes to men, but no to women because 80% of data was regarding the men. So, and rejected tons of qualified female engineers. So, if that time when Amazon was when they were training AI for any kind of recruitment processes for hiring. So, in that case, the women were getting rejected because the data was only built on the AI was only built on 80% of men data. The algorithm was fine. The data was poisoned by history. So, algorithm has no problem, but data was having some problems. So they had to shut it down. So it was in 2018. And that's why I'm telling you why it matters so much is because if you have a bad data, examples, missing values, incorrect labels, outdated informations, and there's a lot of other wrong patterns and fails to like everything kind is like they confusing and very noisy data. So definitely we need to pre-process it for this. So if you are pre-processing any kind of data, definitely that data is going to be very, very helpful for any kind of machine learning models. So 69% of companies report poor data block reliable AI decisions. Definitely. Actually, the numbers could be more than that because data nowadays is very hard to find a good quality of data. Data, you can generate synthetic data, any kind of data, but the model performance is very bad when it goes to the production line. So I'll explain you how the data quality versus what is the model complexity will work in this scenario. So let's say there's a high quality data and there's a low quality data. So good data plus simple model beats bad data. Super complex model every single time. So if you have good data plus a simple model, it will beat any kind of bad data with super complex model. So if you have a very complex model but with bad data, it will definitely get beaten every time. So you need to spend 80% of effort, I would say more than 80%, like 90% of effort on cleaning data, pre-processing it, feature engineering it, and also making it very suitable for the model or the task which you are trying to achieve or goal which you are trying to achieve. And 20% of like fancy algorithms for testing the data. That's it. Not that much on the testing it, but definitely a lot of data you need to use with clean procedure of training the data. So let's say I'll give you a real one example. Let's say Netflix recommendation system, which we all have used it. So Netflix doesn't use complicated AI to guess. So what you will watch is like it looks like what people like to watch, found patterns, and recommended those patterns. So it will recommend those patterns, what you will watch or click on it. So if they have bad data, let's say they record user watched like horror movies, and then they will show you like some comedy movies, like so all horror movies is considered as a comedy movies. So it can be like that kind of scenarios. So definitely you need to have a good structure of data and good quality of data when you're going through it. So definitely simple data with good accurate predictions and good complexity of models, like simple complexity of model, but very good quality of data is very good. So let's say I will give you one more complete. There are three real world examples. Already I've given it of Amazon recruiting AI, and I will give you more too examples. I hope you guys will understand according to that. So let's say there was a healthcare prediction model, which was having 30% of patient records and it was missing data. And that means 30% of the data was missing, which was a patient records. And model invented patterns from gaps. So it was missing the data, so a model cannot understand. So it created its own kind of data or kind of understanding of outcomes for those kind of unfound data, 30% of patient records, missing data. So if you know a patient is sometimes sick, the AI fills in blanks randomly like, okay, this is completely sick. This is not sometimes sick, that person is completely sick. And it's like playing Mad Libs, like, okay, if he's let's say this guy is completely sick and even that person comes and checks that what is his record and it says that you are completely sick at that time or you're having this kind of blood pressure even though the blood pressure was lower but the data was missing that what how much was the blood pressure. It gives you upper and lower like not exact accuracy of the blood pressure, so you can be like come under, if you're on the borderline you can come under into higher blood pressure or you could come under lower blood pressure. So definitely, if you're on the borderline, it can be some kind of more difficult for the AI to get gaps or all kinds of exact accuracy of the information. If you go through COVID-19 disasters, you can see that model was trained on January 2020 data, and total failure by March was everything changed. Like it was completely failure because the model was like a weather app that only saw sunny days, but then a hurricane hits and it says that okay, the model have seen this kind of information, but there was some information missing, some information was not there. So that means that model got confused and they start giving some other information. That's why I give you an example like the it says that there's a sunny, the data says sunny days and the model says hurricane, or model says it's sunny days and data says it's hurricane. So you can see that this kind of confusions and the data gives you wrong information and start hallucinating. That's the problem with not quality of data. So you can see real world examples. Definitely there's a issues going on in this world because you have a bad data. So definitely a data is very important than what model complexity or model is first. Algorithms is later and data comes more. If you don't feed, let's say one very real example, I'll be providing you that what you're eating every day reflects your body. So, like what you eat is a data, body is a model. So, what you feed the model reflects according to that. So, definitely, this is the procedure for everything, even for humans. So, I'll start with what is machine learning. So, machine learning is just by definition, just a system that improves their performance on a task by learning from examples without being explicitly programmed. So this is just an algorithm. Machine learning is a learning algorithm which learns from the data, represents some kind of outcomes according to the analysis of the data. Simple answer is that it's an algorithm. Machine learning is a learning algorithm which learns from the data, analyze the data, and gives us some kind of output. The three components of machine learning: data, model, and learning algorithms. The data is completely what you feed, like information into a textual file, or let's say Excel files, or any kind of Tableau data, or unstructured data, or structured data. It could be anything. Data is any kind of information which you feed to the system. Model, it could be a mathematical structure that captures patterns. So let's say a model could be any kind of mathematical structure algorithms like architecture. Model could be an architecture like what how the models will work and which procedure. It's like a structure. Learning algorithm is the process of that architecture, how those architecture will process system by system. So let's say a model could be uh, a paragraph, or like model could be a level 1, level 2, level 3, level 4, and learning algorithms could be algorithm into level 1 and then algorithm into level 2. So it gives like pass out each level from one level to another level according to the algorithm, and it gives you a better response according to that. So you can understand like this: that data is just information, model is like architecture, how these kind of models will work, and learning algorithms are like algorithms, how inside this architecture what algorithms will work in each section of the architecture. So there are two kinds of base systems. There could be a rule-based and learning-based system. So in machine learning, if you're going through a rule-based, it's very old kind of system. It was used very old times, not into real life. So definitely programmers write rules, and if temperature is greater than 30, then hot. So we're setting a rule. If the temperature is 30, then it's hot. If it's lower than 30, it's medium, and lower than 10 is very cold, like cold. And lower than minus, like 1 degree, in minus degree, it is like snowy. So there is a rule base. It's completely a set rules, but it's not exact accurate because the rules are set according to the probability, what can be happen or what cannot be happen. So it's not an exact findings. Learning based is like it learns from the patterns in everyday basis, daily to daily basis, and then it gives you an output. So let's say system learns rules from data, sees 1000 temperature examples and finds its own pattern, and then adapts automatically. So it learns from the 1000 of temperature examples, let's say 2000, 4000, 5000 on daily basis. Then it finds the pattern, and then it adapts automatically that okay, this kind of learning, this kind of data will come next time. I have to tell according to whatever I have learned are good results. So this kind of learning based models can be more benefit and more useful in today's world than what rule based models do. Rule base is very old because when you're doing it, your HTML, web designing, or kind of, let's say, small application development or programming. So that time you were doing this kind of rule based. But nowadays, when you're doing machine learning, definitely a learning based is better because that's how the machines will understand on daily basis and give you an output without every time providing some rules, specific rules for this. So I'll go through now different kinds of data, what different structure of data. So let's say there's a supervised learning. So in supervised learning, you have a supervised data. So this is a supervised learning is a types of learnings with labels like it has a category. It has just like I told you, if you're giving a cat, dog, and elephant all as an animal. Okay, but let's say you give cat and dog as a pet animal and elephant as a street animal. So this is also a different labeling. So if a data only knows this, these are all animals. If you ask a AI that tell me which one of from these are street animals, it says none of them. And then which one of them are from the pet animal, it says none of them. Or maybe don't know the information, or it just say that all of them. It could predict anything. We don't know what it is because it's not trained. So it will give you any kind of hallucinated responses. So if I'll tell you that simple analogy, let's say data has an email plus label like a spam and not spam. The learning, it's like finding patterns that distinguish spam from legitimate. So if there's a category of some emails is spam and some emails is not spam, it will learn the pattern, which email is spam, on what basis that email is a spam, and on what basis that email is not a spam, like analyzing email, where it coming from, is it a legitimate email, and find text of the email and find any kind of some keywords which is mentioned in the email, it doesn't reflect some kind of attack or some kind of a spam, and find the links if it doesn't affect some kind of spam in that links, so it could be anything like that. So this is how it learns the patterns, and then it predict the new email and classify automatically. So a new email, when it comes, it sees the same patterns, finding the email with the correct legitimate email senders, with legitimate emails, and also the text. It will analyze the text, it will analyze all the wordings of the text, links of the emails. So after those kind of analysis, it will try to classify it automatically. So in supervised learning, there are two types of supervised learning when the models are learning it. One is classification. So let's say in the classification model, and another is regression. So we'll come after classification and regression. Classification is, it classifies that with categories like, oh, this is an email which is a spam. This is an email which is not a spam. So I gave a classification. I classified it. This kind of email should be spam no matter what. This kind of email should be not spam, a legitimate email no matter what, because we have predicted after thousands and thousands of data analysis. So in tumor also, like benign cancer, so this kind of analysis could be benign. This kind of analysis could be a cancer. Image like cat, dog, a bird, like which could be a cat, which could be a dog, which could be a bird, according to our pixel informations and according to our image, what do you call, image length and size of the image, and what kind of structure the cat has and dog has and bird has it, according to the feature. We call it like a feature informations. So in the regression parts, it predicts the numbers. It doesn't categorize completely as a specific category classifications, but it gives a kind of sequence of predictions. Let's say a house price could be $500,000 or could be less or more, or into the $500,000 it could be anything in between. So it's like stock price could be $150. So it predicts numbers, not categorized as labels, but only in kind of continuous numbers, you could say. So if it has a continuous numbers, definitely it could change up and down. So let's say today house price is 500,000. Tomorrow it could be something else. Yesterday was something else. In 10 days it will be something else. But in images, let's say cat, dog, bird, it always be a cat as a cat, dog as a dog, bird as a bird. You cannot change tomorrow. The cat could be a dog or dog could be a bird. Okay, so in the benign cancer also, if a specific criteria for choosing is it benign or is cancer will always remain the same criteria, because in the medical systems, when some person has some kind of illness, everyone has the same symptoms for the illness. There's no different symptoms for different illness. Sorry, different system is different symptoms is there for different illness, but not the same illness. So this is how you can understand classification and regression. So regression is completely which can change over time. Is a continuous. Tomorrow it can be different. Yesterday it could be different. 10 days after it could be different. Classification does not change. It remains very specific and accurate. So in unsupervised learning, it is completely with no labels. So there's no categorizations, there's no regression. This is nothing is there to tell that data reflects this information. Nothing. It's just the data, a normal line data, which is lying on the table form or any kind of form. It's just there and it has no labeling at all. So in that conditions, the learning from unlabeled data is no correct answer given. So a data is just raw customer behavior, no labels. Learning finds like simple groups of similar customers automatically. In these conditions, we try to cluster the data by some kind of groupings. Let's say there's a customers which who likes to buy only computers. So we group the customer. This is a computer interested customers. This is a mobile interested customers. Or this is a traveler customers. They only like to travel. This is a more fun loving customer. This is a more sad customer. This is more customer with lots of cancers. but we don't have data. After you label it, after you group it and cluster it, then you can create a label and a categorization for those data, and then you can feed it to the model, and then model will learn it. So unsupervised, you can convert it to the supervised learning, and then you feed it to the model, and model learns it and completely provides complete good response according to that. And that's how machine learning models are being trained from the unsupervised to the supervised, and then from supervised to a specific machine learning model which can analyze this. So whenever you have, like, let's say, a real world data, it is not labeled. So what you do, you try to train a model which is based on unsupervised. You feed all unsupervised data onto the model. Then that model gives you a response with all kinds of label and categorizations. Then you create a supervised data from that model, fit to a supervised models, and then you get a model which can reflect with categorization every day. So you can do like this also, definitely. Or you can just use unsupervised models and you can get a categorization on daily basis. So unsupervised learning works with clustering examples. So I'll give you very real examples. I have mentioned it in my slides. So you can see that Netflix groups movies with no labels. So definitely movies with find similar genres automatically. It's like a groups. The genre has a group. So there's a horror. So it can reflect you or the horror. So if it's let's say comedy, like if it's a horror and comedy combined, so it will also reflect if you're watching some movie with a horror and comedy combined, it will reflect you in that grouping with horror and movie comedy combined. So you'll have this kind of recommendations, which is definitely in a group form. In the genre is like a group, so everything comes under genre. Genre is completely a group. Inside that, there's a horror. Every horror movies, horror and comedy, every horror and comedy movies combined will be recommended, and any kind of, let's say, comedy movies, all the comedy movies will be shown to you in the recommendation. Spotify also use group songs, so when you're discovering playlists with similar user taste, it will definitely provide you a groupings of that taste. So whatever, let's say you have a melody or romantic or jazz, or let's say a rock songs, or country songs, or let's say what you call rap songs. So you can definitely have a groupings according to that, and it can an analyze and discover your playlist according to based on those grouping songs and similar user tastes. So whatever your taste has, based on that, it will provide you the recommendations. In biology also, if you have group genes sequence, it will definitely have the same kind of grouping for DNAs. So which DNA will have which groupings, it can manage according to that patterns. And fraud detections, definitely in fraud detections, people are using now group transactions. So let's say there's many unusual transactions, and but those unusual transactions can be grouped into some kind of groupings. So I'll give you a real world example. Let's say some credit card holders are there. What they're doing, they're tracking out the money from credit card. They are just telling that the credit card was lost and this and that, you did not use it, or something like unusual information they give it, even though I don't know, like they have used this credit card or not, or someone used it. And then this kind of fraud is getting happens. It can be grouped as a uninformation, or like fake information, or kind of scamming kind of grouping. So there are many kinds of other groupings for fraud detections. People can detect fraud according to lots of attacks. Also, there are latent attacks, fraud detection, which is have different kinds of patterns. Like email detections, where you have a fraud through emails. A voice detection, we have fraud through voice. So definitely, a fraud detections can be categorized into a separate fraud groupings. So there are many kinds of fraud detections nowadays, and there's some kind of honey pot detections also are different groups. So definitely there are lots of them. So if you go through supervised versus unsupervised side by side, supervised is just like a label data required, and it's clear text, defined, predictable output, easy to evaluate, and labels are expensive because you go through uh, lots of process to create a label, and then you try to feed those label to as after creating label, you convert it to the supervised data, and then you use it for the machine learning models. So it's definitely expensive and takes time consuming. Unsupervised, there's no labels are needed and discovers patterns directly. No need to have labels, just discovers the patterns. And then finds a hidden structure and cheap to implement because you just feed a raw data. There's no pre-processing needed for the data. You need to remove the noise and other things, but definitely for labeling, you don't need to pay attention and analyze by yourself or some other ways of other means of uh, other means don't need to analyze. So you definitely is much cheaper. Hard to evaluate results. Definitely, this is hard to evaluate results because if you have a label, it's very easy to evaluate. But if you don't have a label, definitely it creates some kind of little bit difficulty to evaluate these kind of models. So there are different machine learning pipelines. You can go through like if I'll go through raw data, completely raw data which has never been seen or used. It's just a raw data which came from the internet and you're just trying to use it for your machine learning models. Then you start the processing with splitting data into 70% training, 15% validation, and 15% test. So if you want to train more, it is more better. So you can put like let's say 75% training, 15% validation, and 10% test. So testing can be a lesser, it doesn't require, but training is should be more because if you have more training data, it performs better any kind of machine learning models. Then you train those models with the learning patterns from training data. So you train the models and put the data inside the models, and they try to learn through the patterns, and it trains itself automatically. And then after training it, but you need to not just feed the data, you need to also do hyperparameter tuning of those models, because if you're doing hyperparameter tuning of those models, definitely you need to set a parameters, a lot of parameters, and then it will perform more better. And then you can evaluate and deploy those models. Definitely after you trained it, you can evaluate through validations, 15% of data which you have it, and 15% of test data which you can test it also, and then you can put it into deploy in production line for deployment. Why splitting data matters? I told you, like if you split more data, definitely it will train better. So it will increase the accuracy of the training. So if you do not split the data, and if your training accuracy is 95, real accuracy could be 60% only. But if you're splitting the data in a very good performance, a very good way, like let's say 80%, it's, or mostly people do 80-20 or 80 15 5% kind of test data should be 5%, 15% validation, and 80% training data. So 80% training data, 15% validation, 5% test data is much better also. But if you go with 75%, people sometimes go 70% also. So my point is that if you have a proper splitting of the data, definitely the accuracy will be higher and the test accuracy will be also higher. So training accuracy and real accuracy will always be higher if you put in the production line. But it will have difference, but it will have much higher accuracy than what training data is providing it to you. So what does a model actually learn? So a model does not understand the meaning. It's just like I told you in my previous lecture. Model does not understand the meaning. It understands the patterns and weight of the model. Like what is the pattern? What is the pattern of this data? What kind of understanding I can? It understands the model, not like the meaning of the model, but the patterns. This is also an understanding, but there's a difference. Meaning understanding is like you understand each word and you try to analyze each word. These are done by LLMs nowadays, but for this kind of machine learning models, which were used in before training data, that time it's only be used for patterns, not for any kind of meaning understanding. But large language models, which is LLMs, they understand the meaning of the words also nowadays. So definitely the system has improved, but I hope you guys will understand the basic form, what really machine learning models were doing and what it is being done right now through those kind of improved models for large language. They are also like machine learning models, but these are based on large language models. So definitely it has a huge understanding and huge different structures. So this performs more better in a very different way. So in neural network example, I will give you, there's a layer one where it learns simple patterns, edges and lines. When it goes from layer one to layer two, it combines the shapes and curves. It starts learning the shapes and curves. When it goes from layer two to layer three, it starts understanding the objects. Is it eye, nose, cat, dog? It could be anything. And the final it gives you an answer. It is a cat or it is a dog. So if you'll train on neural network, any kind of models, let's say CNN, RNN, or any kind of models, there are many kind of models out there for neural networks. It will always go through layering process, one layer to the other layer for to the other layer for other layer, like three layer, four layer. It depends. But the more layer you'll have, the more computation it requires because and the results will be better. Definitely, results will be better if you have more layers. But the computation also requires a lot more computation for that kind of algorithm to complete finish till the final answer. So you can see in the key points, each layer learns the features, not the concept. So it learns the features. What is the edges? What is the lines? What are curves? What are textures? Or what should, after understanding curves and textures, like edges and lines, what does eye look like, noses look like, and that provides the cat or dog kind of things, you know? So, so feature learning, layer by layer progression, just I told you, layer one detects eyes, vertical lines, horizontal lines, diagonal lines. Layer two combine edges, texture, for texture, smooth textures, smooth surfaces. Layer three understands the combination of textures, parts, ears, nose, paws, and layer four combines parts and then tells you object identity. Is it a dog or a cat? Dog versus cat. So definitely you can see that it goes by layer by layer. So the generalization problem is overfitting. So when you are going through this training, there are some drawbacks and some kind of limitations. And it's a very important limitation is overfitting. So there's overfitting and underfitting, but I'll tell you about the overfitting when the training data starts to have memorized like training accuracy is 98%, test accuracy is 45%. It's very long difference between accuracy of training data and the accuracy of testing data. That means there's some kind of too complexity of the model was too complex that it start overfitting inside all the data are started overfitting. So it was more improving when you were training it and less improving when you were testing it. So it was completely overfit. If it goes to underfitting, at that time in the training data and the test data will also differ a lot. So definitely there's a good generalization where you learn real patterns. Train accuracy is 85 and test accuracy is 83%. After overfitting is taken care of, there's a procedure to take care of overfitting, like removing missing data or like normalizing the data. Definitely, if you normalize the data, it is good because some points could be very high, some points could be very low. So it can create lots of overfitting functions into the models. Because data are completely full of overfitting features, so definitely it will create overfitting functions, a lot of problematic outcomes. So train accuracy could be 85 and test accuracy could be 83, which is very good for if you are not having overfitting. And approximate complexity will be there, not too complex, not less complex. If you have less complex, then underfitting, it could go to the underfitting process. Works on new data, definitely if you fit new data, it also gives you good results. So definitely it's better and it learns on real patterns and everything. So like goes with real patterns. So limits of generalizations is why model really actually fails. What are the limits of generalizations? So in distribution shift, a model trained on summer data fails in winter. So you see, you cannot generalize. The data is good for even summer, winter, spring, autumn, all kinds of weather in whole year. So that's the limit of generalization. So you need to generalize the data according to specific time frame and weather, and specific to distribution shifts from one shift to the another shift. Narrow training data is also like trained on young faces, can't recognize elderly people. So there's a narrow training of the data. It cannot be recognized if the trained on the young faces, young people, it cannot recognize older people. So it has to be more generalization between both younger and older people. Rare events like model trained on 99% of normal cases and fails to predict 1% fraud. So it should be trained on both normal cases and fraud cases combined. It should not be like all you give normal cases, then you try to find the fraud cases. How you'll understand the pattern? If you if you want the model to understand the pattern, you need to provide both normal cases and the fraud cases. And once it provides both, it will understand the pattern completely. What are the adversarial examples? I can give you like a small changes to input can fool models. Example, stop sign plus sticker is equals to car. So actually, when you there's a stop sign plus some kind of stickers which says that stop is equal to car, means like car has to stop. So there's kind of like it can fool uh, the model because if you're providing a stop sign and there's a sticker of a car, it will say, oh, the car has to stop. But even though the stop sign is for all kinds of vehicles to stop. So small changes into one specific stop sign can create a model to get fooled and it can provide a wrong information. So real example, let's say ImageNet success story. So data behind CNN success. So ImageNet data in 2009 had 1.2 million labeled images. From that, 1,000 was categorized as a dog, breeds, vehicle, and objects. And diverse condition was different angles, lighting, and seasons. So what results was found in that ImageNet dataset in 2009, which was having most people have used it for training also, that AlexNet in 2012 had 85% of accuracy, sparked deep learning revolution. So they have less high quality, large models with large diverse data they have used to train the models, and it was having a revolutionary results. When it comes to ImageNet, it was only trained on 1,000 categories with 1.2 million label data. It has a diverse conditions like different angles from it. So definitely, if you have a good quality of data like ImageNet dataset, you'll have a result completely 85% accuracy. So it took like from 2019 till 2022 to train these models with so much vast quality of data that it starts giving a revolutionary result. So there are biases in training data, a critical issue. So there are facial recognition. I'll give you an examples. The model inherits biases. So biases is very important to fix it. There's a facial recognition. So train more mostly on light skin faces. 35% of the error rate on dark skin. So if you're training on light skin, you're getting a bias of 35% error rate on dark skin. So you need to train without any biases in the data for both light skin and the dark skin. Lesser language models, they are trained on internet text but amplifies gender stereotypes. So in that case, you need to provide language models less biases. So if there is a gender questions, you need to be completely more formalized into gender. You need, no need to be so much stereotypical responses. So you need to provide this kind of fixing in the biases for large language models when you some people is trying to ask the model about some sort of gender specific information. So definitely it amplifies gender stereotypes if you're providing that information. Hiring system. So when you're using historical data plus discriminations, that time people will start having some perpetuality hiring biases. So let's say a woman is going, AI is saying that no, we will not hire the woman because we are trained on only men data. Because I told you about the Amazon problems which were having with AI when they were training it with only men's data. So definitely there is a hiring system where they have biases in that system with historical data plus discriminations about if this data is only trained on women, it can be having a biases of male. When male is going, it stops. Like tells no need to hire or just discard all the resumes of the males, not matching the requirements or not matching the trained data accuracies. So this is very important, very, very important. What are the data collection best practices? So it could be like representation data include diverse cases where age, race, gender, and conditions. So if you have a diverse cases data, it's very good when it represents data with full diversity and it gives the model full information about each section of the data. their data collection best practices. We were going through it like sufficient size generally need 1000 plus samples per category minimum. So I would suggest like if you are having more than 1000 plus samples, it will be much better because the more size of the data is the better for the model to understand everything. You need to have a clean labels like careful annotations, multiple reviewers for important tasks. So you need to have completely a clean labeling, categorizations of each data rows and you have to provide each data with a good labels. So that if the labeling is completely clean and accurate, definitely the model will behave according to that. Documentation definitely is much more important because you need to record how data was collected and metadata definitely matters. So, what was the data quality? What was the data? Where was it collected? And every kind of documentation you need to have it. Regular audits definitely you need to always monitor model performance across different groups. Let's say you are providing some data, new data, and you are trying to see its output. You need to also monitor it. So how is it performing? Is it performing good or bad? According to the different variations of data. So you can see the outputs according to the variations of data. So in feature engineering, you need to prepare data. So in that case, you need to normalize first, and the scale like you need to have a scale of 18 to 80, and income like 10,000 to 1 million to some range. Like it's just like a normalization. So in this range to that range, it should normalize the data. It should make it because data could be more than 80, let's say 90, 100, and more data could be more less than 18 also, or data could be more than like in between also. So you need to normalize it the average how which data are more into average range. So in that range you need to normalize the data. You need to do encoding categorization. So you need to convert color like for the images. So if you to convert color red, blue, green to some numeric model understands like sometimes when you are trying to build a model for images, you need to also convert the colors into a grayscale. From after converting to grayscale, those models can easily be trained on the data because coloring sequence have more pixelation and more like more quantity of sizes of the data. So definitely if you can convert the color into more numerical format, it will be very easy to for the machine learning model to understand because that's how the machine learning model understands. You need to encode the category of the categorical columns to a numerical format for understanding. You can handle the missing data. Definitely, you should handle the missing data. Whenever data is not available, you need to fill the gaps. Or if the data is available and it's not correct format, so you need to mix it, fit the format and everything. So it's like a feature selection, like how which feature should be more appropriate for. You cannot put all the features into the data, and then you can put it into feed it to the training for the model. You need to select the feature according to the requirements. You need to remove the noise and duplicates of the data. So these are all pre-processing and feature engineering techniques which we can use it for before you trying to feed the data to the model and train it. So this is a very good question. Let's say you say, how do we measure model performance? So what are the parameters or criteria to measure the model performance. So through measuring model performance, you can measure through different criteria. There are many different. These are the more important ones, which all models should be having it, and you should measure it from all perspectives of the all models. Accuracy, definitely you should measure accuracy of the model. How is it performing? What percent of correct predictions is predicting it? And what are the works for the balanced classes? Or what are the accuracy for each classes is they be able to perform higher accuracy or lower accuracy. You can also measure a performance with precision and recall when false positive is high or is it low or according to the negatives and what are the like precision and recall for the false positive and negatives. So you need to see, yeah, it runs with the true positive, true negative, and how this kind of true positives and true negatives and false positives and false negatives perform. Yeah, you need to also go through that thing for accuracy of the and performance of the model. For F1 score, definitely you need to find a balance between precision and recall. So that's how F1 scores are found. So if there is a balance between precision and recall, your F1 score will be good. And if it's good, that means your model performance is better. So, and there's a awk and rock. Auxiliary and awk and rock. So this is known as how well model distinguishes between classes. So let's say there's a two classes or three class models where you have trained the model with two classes or three binary or multilinear models where you're putting more than two classes or binary models where you're putting two classes only to train the model. So how they are distinguishing between classes is the classes are completely good, have a good distinction, or is it like a little bit overlapping in between them. The pattern recognition ceiling, definitely what models can't learn. And there's a casual this. Why not just what happens? Like if models learn everything, everything works good for it. But there are some scenarios where models do not learn it. And that scenario is like in that case, they have a common sense. A model cannot understand common sense. Casualties, model cannot, causalities, model cannot just understand what happens like right now currently in recent times. So because those events don't have data in fed to the model already, so obviously these similar data should be fed for the testing. You cannot put a data from medical to some kind of from management. So if there's a data of management, you cannot put a medical data into a management models and you expect the model to perform better. There are rare events if it never appeared in the training data. So definitely the events are very rare. And if it never appeared in training data, then it will be have some problems with the models to learn and to understand and to again give you a good output. Out of distribution, so it's completely new situations. If you're putting a new situations to the model, and I just like I said it to you, like if you're putting medical data to a management model, it will definitely not work. And if you're putting management data to the medical model, it will not work also. So it's completely out of distribution, it's not expected at all. It's completely new situations you're putting it. It's not going to work out. Reasoning chains, definitely there's a multi-step logical deductions. So you need to check what kind of logically a model can understand things or not. But I say that there's no multi-step logical understanding by the model. So model cannot understand a multi-step. It can understand a singular step. Okay, you need to perform a categorical findings. You need to find if it's a dog or a cat. But it cannot understand that if the dog is there, what kind of breed of dog is this until the data is fed. So this is how it works. So technically, a model learns statistical associations but not underlying concepts. When pattern recognition fails, so when you're self-driving car and it fails. So at that time, your pattern recognition fails and it's very risky, very risky. So let's say Tesla crashed into a white truck at 4 p.m. A car confused truck with bright sky. Understand? Like because of the too much light, too much something, there is a confusion for the pattern recognition for the detection of the AI. AI cannot detect because let's say you're using a phone. When you're using a phone, you're trying to do your face detection for unlocking your phone. At that time, there's no light. At that time, there's no light, so it cannot even see your eyes or see your face nicely. So definitely this could be a problem. So if you have some one eye problem and you are closing one eye and one eye is open, so it also stops. It doesn't detect at all. It gets confused. So an adversarial example is like add tiny noise to images. So a model flips answers, and so if you add a little bit of noise also to the images, you'll have some kind of pattern recognition failures. A spurious correlation, so model learns grass is equals to cow, and because training images have cow in fields, so it will start getting confused. So grass is grass, but grass is not a cow. A cow is not a grass, so definitely a model will have some kind of confusions because the grass is in the field right now, and it cannot differentiate if it's a grass or it's a cow. Maybe a cow can be it's saying cow is a grass, or sometimes it's saying that grass is a cow. So when you're recognizing or detecting an object, definitely an AI model can create some kind of confusions by themselves, and then it will give you a wrong information, a wrong answer, a wrong detection, recognition, any kind of things you could be wrong. So in this module, we will take a key takeaways or like data is everything, everything, like every and everything. What you feed, just like I told you, what you eat, you build yourself like that. So you are like what you eat. So just like that in the AI also, what you feed the AI with the data, the AI performs according to that. Algorithms matter less than data quality. So algorithms is very less. What you feed the algorithms will run according to that. So what you give the data, data is like a food to the AI. Just like we are eating whatever we eat, according to that, our body reflects or behaves. So algorithms matters less than data quality. So needs very good data to work more better. If you feed the wrong data, it will not work that good. If you feed poor data, also it will not work good. So you need to have a good quality data with good amount. Supervised versus unsupervised, different tools for different problems. So you need to have understanding which one to use at what time. Generalization is hard, definitely. Models learn training data, not universal truth. So they just learn the training data. If you putting a data from summer, they cannot tell the weather of winter. If you're putting a data of winter, they cannot tell the weather of summer or any other weathers like spring or autumn. So definitely, generalization is very hard. So you need to put the data of all the situations what you need. Pattern recognition has limits. Completely, definitely, it has limits. Can't learn casualty or reasonings. Test on unseen data. So you can test on unseen data only real validation of model quality. So if you're testing on unseen data, then there's a problem with the data that a data can reflect with lower accuracy because this data was never seen before by the model at all, not trained by the model, is completely reflective. Just like I give an example about medical and management. If you're using anyone's model and other one's data, definitely it is going to not work because data is completely unknown for the model. Because if you're using a medical model and you're putting a data of management, and you're using a management model, you're putting a data of medical, it's completely getting a new variety of information and it's not been trained on before. So definitely it will have a problem if you're not been trained on before. So and the supervised versus unsupervised, and these different tools should be used for different problems, and you need to analyze. If you want to analyze a categorical, if you're doing for dog and cat, definitely you need to go with supervised categorical. If you're doing it something a data doesn't have label at all, unsupervised. If you're doing something for continuous values, you need to go for supervised regression models. So now you understand machine learning fundamentals and you understand what is data, how much is important, what is learning, how machine learning learns, generalization, how generalization is important. And we have given also, I have given you real world examples, a lot of them. So definitely you got a lot of overview and other kinds of foundations of machine learning in this lecture. And you can see that from next lecture, next module, we'll go with common failures and mistakes of artificial intelligence. What are the common failures and what are the mistakes of artificial intelligence? So you can comment down below with your questions, and we'll definitely I'll answer you on the basis of your questions. Definitely, I'm going to answer you everything. So thank you for attending this lecture, and please come to the next lecture also. I hope you will enjoy this mini course, and this is definitely very good for anyone who's from non-tech or who's from any kind of school children or anyone. I'm trying to teach something in very low and very understanding with real world examples scenarios. So I hope you guys will understand. And if you understand, please comment down below how is it this lecture. I hope to see you guys again in the next lecture. Thank you. Bye.